This is the final part of Experiment 6 lecture video. Um, so this is the combinatorial synthesis of azo dyes. So part 1 of the video was talking about what combinatorial synthesis is, and part 2 was getting into this idea of what does it take for an organic molecule to absorb visible light. So now we actually get into the synthesis that we're going to be doing. And um, thinking about it, that what we eventually want to get to is we want to convert aromatic anilines into these diazotized aromatic molecules. So that's really the goal here. So what we're going to do is take hydrochloric acid plus sodium nitrite and form HONO. Um, and once we form that reactive intermediate, then that's going to react directly with the aromatic anilines to give you intermediates that look like this. And I'm not going to go through all the mechanistic steps of how we get to the diazotized molecule at that point. But really the key is that we want to get to this diazotized or or aromatic molecule that's derived from this organic aniline. So that's really the key that you need to keep in mind here. And then once we have this diazotized version, this, as it turns out, is an outstanding electrophile that will react with other aromatic nucleophiles in chemistry that will look very similar to the Friedel-Crafts chemistry that you did before. So again, once we have our diazotized um, aniline molecule, if we take any activated aromatic system at that point, so here we're showing that this aromatic system is activated with nitrogen in the form of an aniline, but really this activation can take any form. We could have like a dimethylamine here, or we could have a hydroxyl group in the form of a phenol, or we could have a methoxy group here. But just anything that's going to activate this aromatic ring towards acting as a nucleophile. So if you go back and look at your Friedel-Crafts um, aromatic substitution chemistry, and if you've gotten into aromatic substitution, anything that's going to be an activating group is going to cause this reaction to happen. So you'll have your aromatic system acting as a nucleophile to attack this outstanding electrophile, this diazotized electrophile. And then what you get out of this is two aromatic systems still in conjugation through this diazotized system. Okay. So some important diazo dyes, um, very common red, a very common brown, and absolutely the most important by far is Cheeto orange. Other common diazotized dyes, and other organic dyes that you'll see. I think that the important thing to keep in mind here is that for the most part, in all of these cases, you have these long extended conjugated systems. So if you go back to the video part 2 and understand why having long extended conjugation is important to getting a molecule to absorb in the visible range, you'll understand why these molecules typically look the way that they do. Even within the lab, you see a good example of a diazo dye. So this is for pH 4. The diazo dye here can be protonated under low pH, and that you can get a molecule that looks like this. where it still maintains conjugation, but the conjugation has changed a bit, right? Because you're going to protonate this nitrogen, and you still have conjugation throughout because this lone pair is still going to stay in conjugation with the whole system. But by protonating that, you just change the overall aromatic system, and that changes the wavelength of light that it absorbs. Okay. And here is a great slide that you can't really see all the details of it, so let's just kind of skip it. The premise of this slide is to talk about how long the conjugation is in an organic system and how you can correlate that to the wavelength of light, i.e. what color light. So getting us into the experiment, we have 4 different anilines that you will be potentially diazotizing. You'll get assigned one of these, but you're going to find out that this experiment is actually quite efficient, and if you want to do more than one di, it will be no problem. But you're going to make the diazo substance, you're going to make the diazotized aniline, and then once you form that diazotized aniline, you will then add one of these activated aromatic systems. 3 of them are naphthalenes, and one of them is a benzene derivative. And these will all react with the diazotized anilines. And what you're going to find is that these are then the building blocks that you can use to form around that central diazo core. So if you have 4 building blocks on each side, and they're all going to come together in that central diazo core, so 4 times 4, the permutation is that you can get 16 possible molecules. So once you make those molecules, you are then going to dye some fabric swatches that we have. And these fabric swatches have different types of fabric, including acetate, cotton, nylon, Dacron, Orlon, and wool. And we have also provided the structures of these, and an important part of the lab write-up is going to be able to try to make hypotheses as to why it is that certain dyes will dye different fabrics better. And then with the whole class, we'll end up making all of the dyes here, and then you can make multiple dyes. Okay. And again, this is usually a pretty efficient lab, and so people should be done absolutely on time, if not early.